Okay, so in the previous session, we actually were discussing about the definition of bivariate distribution. I'm not going to repeat the definition here in the beginning of this session. Let's get back, let's go to the problem directly and let's study the problem. Meanwhile, you write your roll numbers in the chat box because that is essential for your attendance. I have selected this particular problem from the book itself, from the John Point book, and I have elaborated the problem in this particular note. So probably you are seeing that the thing which is over there has not been typed by me. I have directly pasted the thing, but the generalized the elaboration will be shown to you in the subsequent pages. Okay, so let's study the problem as it is given in the book. Let us try to discuss let us try to understand what the bivariate case is and what is its joint probability distribution. So the problem goes like this. Two caplets are selected at random. Caplets, what does it mean? Caplets is the general term for either tablets or capsules. Two caplets are selected at random from a bottle containing 3 aspirin, 2 sedative, and 4 laxative caplets. If capital X and capital Y are respectively the numbers of aspirin and sedative caplets included among the 2 caplets drawn from the bottle, find the probabilities associated with all possible pairs of values of capital X and capital Y. 3 different types of variables were actually present in the problem. Try to understand. One is the variable associated with aspirin. One is the variable associated with sedative. The another is the variable associated with laxative. But we are not interested in the appearance of laxative caplets, and so we have not introduced the variable Z over here. Since we are only interested about aspirin and sedative, so we have introduced 2 variables, capital X and capital Y, and therefore this has become a bivariate case. When the caplets are drawn, 2 caplets are drawn at random, we are counting the number of, and we are drawing the caplets from the basket arbitrarily, and after that we are actually counting the number of aspirins we have got and number of sedatives we have got. That count of number of aspirins and number of sedatives will actually be the count associated with the random variables in this particular case. So to begin with, you can write that has not been written properly in the book, that let capital X be the random variable associated with the count of aspirin, and capital Y be the random variable associated with the count of sedative. Let us try to identify what can happen in this particular scenario. If we do so, what are the possible pairs that can be obtained? What are the possible pairs? After getting after defining the random variables, we can see that 2 tablets have been drawn, but none of the tablets is from the category of aspirin or sedative. So there is one situation where we are getting no aspirin and no sedative. So the pair is, one possible pair is 0, 0. Suppose it may so happen that we have got 1 aspirin and no aspirin and one sedative, that will be similar to the pair 0, 1. One aspirin and no sedative will be the case 1, 0. One aspirin, one sedative will be the case that is 1, 1. No aspirin, two sedatives will be the case 0, 2. Two aspirin, no sedative will be the case 2, 0. And not only this, nobody can understand from these pairs, as is mentioned in the book, that which is what. So not only we define the variables associated with the situations, we also have to say that let capital XY be the pair representing number of aspirin and number of sedative. If you write it in explicit way, then everybody will understand from your tabulation that which represents what. Okay, so as you can make your things as clear as it is possible to understand and to proceed with. Once we tabulate all these values, we try to find the probability associated with these values. And here also, and as you see, if nothing is mentioned, we always call the system to be unbiased. Okay, so that we can apply the so-called classical definition of probability for each case, which is of course a special case of axiomatic theory. Now, let us try to associate the probability with the case 1, 0, and that is being done arbitrarily. The same mathematics can be applied to each and every other case. You are going to see the what kind of table I have formed. I have formed to show you the entire chart in its explicit form. But first of all, let us try to identify the probability associated with this particular thing. Here in this situation, you observe that we are concerned about an event of getting one of the three aspirins, because we have three aspirins in our case and none of the two sedative caplets. But you know that actually we are to get two caplets. So if one is aspirin and other one is not sedative, then obviously the second caplet falls into the category of laxative caplets. Okay, but yeah, I'm not mentioning this in the bracket, because if I do so, that will not remain as pair. It will become a triplet and a trivariate case. We are not interested in trivariate here. We are interested in bivariate. We are only counting aspirin and we are only counting sedatives. And if this is the scenario, this one aspirin tablet can be selected from three aspirins in 3C1 ways. For each of these ways, 0 sedatives can be selected from 2 sedatives in 2C0 ways. If for each of the two ways, for each of these two ways, another tablet, the second tablet can be selected from the laxative in 4C1 ways. And by the multiplication theorem of counting, you know that total number of ways by which this can be achieved is 3C1 multiplied by 2C0 multiplied by 4C1, which gives you 12, which gives you the favorable number of case here. And since we are interested in two tablets, to find the total number of case, we are writing 9C2. because there are 92 ways by which two tablets can be drawn from the basket of tablets, and there are only 9 tablets over here. 4 plus 3 is 7, plus 2 is 9. So 36 possible ways are there by which it can be done. Now it is mentioned that since those probabilities are all equally likely, because as I have already told you that the situation is considered to be unbiased, by virtue of the assumption that the selection is random, it follows from a theorem, and that theorem, which is written in the bracket, it has been proved in one of the pages of the first chapter of the John Freund book. And this so-called PA equal to n by n is what is known as the classical definition of probability. Okay. So the possibility associated with 1, 0, the probability associated, sorry, not possibility, probability associated with 1, 0 is actually 12 by 36, which is 1/3. And similarly, the probability associated with another case they have shown 1, 1, it is 1 by 6. I have shown here all the possible cases, and their respective probabilities have been calculated in an explicit way to show you the total picture, because the total picture is not shown in the book. So I have made a chart, and this is what you are supposed to do. So I have written here calculation of favorable events and probabilities for the pair of random variables. In the chart, I have mentioned how many aspirins are there, how many sedatives are there, how many laxatives are there. All the outcomes have been tabulated. The outcomes we talked about in the beginning of the problem. And the favorable cases have been considered. The favorable cases have been calculated the way I have shown, I have discussed just now. So for 0, 0, we have got this. For 1, 0, we have got this. For 0, 1, we have got this. For 1, 1, we have got this, and so on. And for each of these cases, the total probability, a total case is 36, which is 92. And since the situation is unbiased, second column values have been divided by the third column values to get the respective probabilities. Now, after doing this, what you can do is that you can justify the fact, you can verify the fact whether your table is complete or not by adding all the probabilities together. If your probability, if your sum of the probabilities is not coming out as 1, and I hope that it is 1 in this case, you can verify that as well. Now, if it is not 1, that means your probability chart is not complete. And that means, in turn, that one of the outcomes have not been considered, which was supposed to be considered. But if it is 1, then your distribution chart is complete. Okay. And they have shown, according to the books, according to the book, if I try to tell you what is happening, as shown in the book, that this matrix have been considered. In this matrix, a column has been taken, which is X, associated with the random variable capital X. And this can have values like 0, 1, 2. And Y, this can have values like 0, 1, 2. Now, at this point, I want to stretch your attention towards the fact which I discussed in the previous session, that when I wrote this multinomial distributions definition, I wrote that the random variables associated with that will have values x1, x2, xk, and each of these xi's will have values from 0, 1 to up to n. Now, this fact has been used in the following table, as you can see. I'm trying to correlate what has been taught to you earlier with what is being shown right now in front of you. And what we have done from the chart that we have calculated, we are putting the probabilities in this manner. So for 0, 0, we are putting the probability like this. For 0, 1, we are putting the probability like this. But only thing you have to keep in mind that since you have put X on the top and Y on the left, according to the book, there is no hard and fast rule. One can put X on the left and Y on the top. But since you are going to, you are actually following the John Freund's book. So you have to be acquainted with the notations used in John Freund book. Since they have used X on the top and Y on the left, so you are going to read the column first and then row. Our usual approach is what? To read row first and then column. So here you are going to do the just the opposite because of the way it is written on the chart. And then you can read the table correctly. So this will not read 0, 0, we'll read 0, 0. We'll read 0, 1, 0, 2, 1, 0, 1, 1, 2, 0. This is my case. And a brief thought to the respective probabilities that we have obtained over here in this fourth column will help you to find out that it can be regenerated with the help of the following formula. Very simple formula, of course, where we are calculating fxy. Fxy is the probability. Denominator is, of course, same, which is 9c2. And in the numerator, you are getting 3cx, 2y, and 4, 2 minus x minus y. Why? Because 2 has already been selected. 2, we are interested in 2 tablets, you know. And x can take value from 0, 1, 2. Y can take values 0, 1, 2. Only thing we have to keep in mind that this x plus y, the addition of these two must lie within this 0 and 2, 0 and 2 inclusive. You cannot consider things like 1, 2 or 2, 1 or 2, 2, because in that case, the number of tablets will be greater than 2, but we are not interested in that. We are only interested in 2 tablets. So that is also a condition. So what I'm trying to tell you about is that situation is very simple. I am not trying to find out the solution of the problem. I have not found the solution of the problem by myself because it is already there in the book, but I have elaborated the thing properly. What you have to identify is that when we talk about that a system is following certain probability distribution, I have often seen the teachers, when they introduce probability distribution in the classroom, they say that there are 2 probability distributions. One is discrete, another is continuous. Discrete can be categorized in this, and this way, and continuous are categorized in this and this way. And when we talk about, and after that, when we get a problem, we only think that, yeah, okay, this is we have binomial, we have Poisson, so we have to think in that line. We have this normal, we have uniform, we have to think in that line. This is not the case. Binomial, Poisson, normal, uniform, exponential, gamma, Cauchy, geometric, Bernoulli, negative binomial, hypergeometric, all these things and many more are well-known probability distributions that were studied at some point of time. It doesn't imply that all probability distributions have been studied. There are situations where probability distributions cannot be found. These are actually called non-parametric cases. For example, suppose there is a construction, there are constructions going on in our Salt Lake area, throughout the Salt Lake area. Say metro construction is going on. And it has been observed that the temperature of the Salt Lake is much more higher than the temperature of other parts of Calcutta. So if someone asks that is this temperature variance in the Salt Lake is because of the fact that there is global warming, or is it due to the construction which is going on in the uh, in the in the Salt Lake area, then if the question is asked to a layman, opinion will vary. But if the question is asked to a uh, person who is, I mean, who knows probability theory, then his approach will be different, and he will sit and he will try to collect data and will sit do some calculations and will try to reach to a particular solution. But see, in this situation, you are not able to find the parameters which will justify the case. Such a case is called non-parametric case. Parameters cannot be found. This type of situations are also studied in probability theory. Although they are not there in your syllabus, but they are studied. So the thing is that finding probability distribution is not an easy task to do. If we can get hold of the total sample space, probably we can find the probability distribution. Otherwise, it sometimes becomes very impossible. The situation which has been shown to you just now, that situation is a very simple case, because it is a case where finite number of values associated with the random variables are there. We could find the probabilities, so we could find the formula. And obviously you see that formula, so case is a bivariate case, so no way the formula can be, this is not falling in the domain of the probability distributions which have been discussed so far, because those were univariate cases. This particular formula, if you ask me whether does it have any name or not, the answer is no, it doesn't have any name. This is the case, so that is the formula. But this formula is actually showing you a valid probability distribution, and therefore we can at least say for this Kaplet's problem, a valid probability distribution has been. We are able to find a valid probability distribution in this current situation. Remember, you can ask any question about the system. The questions are not ridiculous. The answers which are given, they are sometimes ridiculous, isn't it? Now, the more sane answer can be produced. With respect to more sane answers can be given to a particular question if your experiment is authentic, mathematical, logical, physical, and it is, I mean, what shall I say? It is possible to perform such experiment. It is possible to get manpower, to get money, everything, to do the pilot survey, to reach at certain conclusion. Anyways, so that is how a probability distribution is found. So now, once the probability distribution is found, and just like we did in the univariate case, after learning about the probability distribution, what did we do? We actually try to find out their properties. Now, first of all, the definition of the joint probability distribution is given over here. Obviously, it is called a joint probability distribution because it is actually, the formula is having two variables. One is small x and another is small y, associated with capital X and capital Y. So the joint probability is defined in the following way, that if capital X and capital Y are discrete random variables, the function given by fxy, this for each pair of values xy within the range of capital X and Y is called joint probability distribution of x and y. And the properties that these probabilities will satisfy is similar to the properties that is satisfied by the probabilities in univariate case. In univariate case, what properties we have? In univariate case, we get the properties like fx is non-negative always, and summation over x fx is equal to 1. Just try to look at this. Similar thing has been obtained over here. Only difference is that in place of fx greater than or equal to 0, we have written fx comma y greater than or equal to 0 for each pair of values xy within its domain. And instead of writing one single summation, double summation has been taken into consideration, and we have written double summation x, double summation y, summation x, summation y, fxy, which will when added will give you 1. Okay, so sometimes just for the sake of your knowledge, sometimes in some books you may find that they instead of writing this double summation, they simply write x comma y fxy is equal to 1. This notation and this notation, they are same. The authors who are using this notation, they are only saving some space. And with respect to our above problem, actually what you are getting, if you add from x equal to 0 to 2 and y equal to 0 to 2, and if you write fx, if you consider the values fxy in the above problem that we have discussed, you'll find the total probability is 1, which has already been checked. That is being written over here. So in bivariate distribution, just like the univariate case, these are the two fundamental properties that the probability function satisfy. Okay, I hope you are understanding. But this concept of bivariate distribution is something which is very new to you. Okay, now so here is a problem. The problem which we have just is another problem that has been taken into consideration. Yeah, I have copied this particular problem from the book. It's from the exercise 42. So I have tried to solve this particular problem for you. So I have copied the question because just to save my time, because nowadays I am typing lots of things that sometimes I become extremely tired. So if the values of the joint probability distribution of capital X and Y are as follows, here also you are going to read it from top to left. What will be the probabilities in this case, in these scenarios? Probability of X equal to 1, comma Y equal to 2. Probability of X equal to 0, Y lying between 1 and 3, 1 inclusive, Y exclusive. X plus Y less than or equal to 1, and X greater than 1, Y. How to calculate these probabilities from this particular chart? In the previous example, I have already told you how to form such charts. Now I'm going to tell you how to use these charts to calculate the respective probabilities. So let's see whether I have typed it or not. Otherwise, I'm going to do the calculation. And if it is typed, then I'm going to okay, it is already typed. So probability of X equal to 1 and probability of Y equal to 2. Only one value X is taken and only Y is taken only one value, that is 2, which can be directly read from the table. So at X equal to 1 and at Y equal to 2, the probability is 1 by 20. So the answer is 1 by 20. So we have noted the probability from the chart itself directly. Let us come to this part. X is having the value 0. So we'll stick to that column. And Y is having the value, Y is having some values from 1 to 3, but 3 is not included. So X can take value, Y can take value 0. Y can take value 1 y can take value 2, but not 3 and not 0 because of the way it is written. So let's see what I have done. So you see only 2 cases are there. So how to write it these cases, that is very important. So probability of x equal to 0 and probability of y equal to y lying between these two is containing 2 cases only. So one case is this, that x equal to 0 and y equal to 1, or x equal to 0 and y equal to 2. Now or is represented by union, so we have placed a union sign over here, and then we are calculating the probabilities. But you know, these cases are mutually exclusive, and therefore that I had that thing which I have not written over here, because I suppose that you know it. The probability of the union of two mutually exclusive events is the sum of their respective probabilities. So it will be probability of this plus probability of this. Now you can read the value directly from the table. And when x equal to 0 and y equal to 1, the value is 1/4. When x equal to 0, y equal to 2, the value is 1/8. And the two values have been added to get the probability. Next is the case where we are going to find the probability that x plus y is less than or equal to 1. So here, the limits of x and limits of y are not given separately. Instead, what is given, that you consider the values of x and values of y in such a way so that the sum total of their values must be less than or equal to 1. So we can take the value 0, 0, in fact, because 0 plus 0 is less than 1. We can take the value 0, 1 because it is less than 0 plus 1 is 1. We cannot take the value 0, 2 because 0 plus 2 is less than 1, is not less than 1. We cannot take the value 0, 3 because 0 plus 3 is not less than 1. Similarly, if we come to second column, we can take 1 plus 0 because it is less than 1, but we cannot take 1 plus 1 because it is greater than 1. And we cannot consider the last column because in the last column, we have 2 plus 0 and 2 plus 1. Both the cases lead to a situation which is greater than 1. So we have got how many cases? We have got 3 cases: 0, 0, 0, 1, 1, 0. Let's see. So C. So that has been written, and they are mutually exclusive, and therefore the probabilities have been directly written from the chart and have been calculated accordingly. What was the next problem? X greater than y. Now, obviously, in this particular case, you have to consider the values where x greater than y. Now you see this case, how can we get it? If we take value of x to be 0, then this situation will not arise at all. Because in each case, now you cannot say that 0 is greater than 0. It's not true. But this case will not be there. 0 is not greater than 1. It's not greater than 2. It's not greater than 3. So none of the cases will come over here. Go to the next column. That is 1. X equal to 1. Now if you take x equal to 1 and y equal to 0, that is true. 1 greater than 0. But if you take x equal to 1 and y equal to 1, that is not being satisfied because 1 is not greater than 1. So only one value has been obtained from here. Go to the next one. Take x equal to 2 and y equal to 0. So here 2 greater than 0. Satisfied. X equal to 2, y equal to 1. 2 greater than 1. Satisfied. So from the third column, all the cases are being satisfied. How many cases we have got over here? 3 cases. This. These probabilities will be added. Let's see what I have done. See. So the mutually exclusive cases in this scenario are x equal to 1, y equal to 0, or x equal to 2, y equal to 0, or x equal to 2, y equal to 1. They are mutually exclusive. Their respective probabilities will be added. And the probabilities are calculated in the following manner, which is this. Okay. And here the distribution function, joint distribution function of the, just like we actually wrote the joint distribution function for univariate case, we defined joint distribution function the same way it has been defined for bivariate case. Just try to recall what was the joint distribution function for the univariate case. In univariate case, the joint distribution function was this. In the bivariate case, the joint distribution function is written as this. Just try to correlate the two things. Okay. And lastly, let's see what is there in this note. Okay. I have shown you the problem. The problem, probably this is the problem that I calculated in the in the previous pages, the laxative tablets and sedative tablet problem. So I have shown here, and I'm going to upload this note in the YouTube, in the Google Classroom, that by the definition of this joint probability distribution, how to calculate the joint probabilities in this case. So all the joint probabilities have been considered, calculated over here. Okay. And I have not shown all the probability. I can see that I have not shown all the probabilities. I have just shown two of them, F00, F01, and F11. Some dots are actually put over here. You can see these dots because I have not calculated F10, I have not calculated F12, F21, 22, 02, 20, that those things have not been calculated. I have left the things to you to calculate by yourself. And if you do so, at the point F22, when you are at the point when you are going to calculate the joint probability, the distribution function F22, the result will come out to be 1, because you know the final value of the joint probability distribution is equal to the total probability. So I'll ask all of you to complete this chart, this calculation by yourself. Okay. Only 3 sample calculation have been shown over here. And one another problem has been, I have given you for you to solve by yourself. So I'll upload this note in the Google Classroom today, and along with the video in the YouTube. So hope to see you tomorrow in the scheduled time. Okay, I'm concluding my class at this point. So tomorrow we are going to meet again. Till then, bye.